Return trip from AVA Memorial to Table Rock. Let's say we've spent enough money at the pilot supply shop at AVA Martin Airport and have decided to return home before our airplane becomes too heavy for liftoff because of all the pilot toys, headsets, computers, flight cases we've purchased. We call the flight service station, and they tell us the winds are from 350 degrees at 30 knots at all altitudes below 10,000 feet MSL. Let's follow the same 6 flight planning steps we performed before and fill out our flight log as we go along. We'll use 120 knots for our true airspeed on the return flight to get home quicker and play with our new pilot toys. Flight Planning Step 1. Draw a line between checkpoints. We've already done this in Figure 35. Flight Planning Step 2. Determine the true course. The true course from AVA Martin to Table Rock is the opposite of what it was for the initial trip, which was 060 degrees. We'll put 240 degrees in our flight log form as shown in Figure 43. At this point, we can quickly determine the magnetic course to see what altitude, even or odd, to fly. Remember the acronym TVMDC. Correcting the true course, 240 degrees, for magnetic variation, 4 degrees east. It hasn't changed from our first flight. We obtain a magnetic course of 236 degrees. 240 degrees minus 4 degrees east equals 236 degrees. According to FAR 91.159, when flying a magnetic course of 180 degrees through 359 degrees, we need to fly at even thousands plus 500 feet, assuming that will be more than 3,000 feet AGL during the flight, which we will be. Since AVA Martin's altitude is 1,131 feet MSL, we can fly at 4,500 feet, 6,500 feet, 8,500 feet, and so on. No sense wasting all that fuel in climbing high for such a short flight. For the purposes of this example, let's fly at 4,500 feet MSL, putting us more than 3,000 feet above the surface. Realistically, I'd probably fly at 2,500 feet MSL on this flight, meaning that I am not restricted by the hemispherical cruising altitudes. We'll add these values to our flight log as shown in Figure 43. Flight Planning Step 3. Determine the wind correction angle. Let's use our flight computer to do this. Using the wind side of the slide computer, set the computer's grommet on the 100 arc before starting a wind problem as shown in Figure 44. Erase all the other wind marks from previous problems. I hope you used pencil, not indelible ink. Make it a point to use a soft lead pencil. Hard lead pencils require you to take running stabs at your computer to make any type of visible mark. Besides, you could accidentally pole vault over your desk. Step 1 says to place the wind direction under the true index. Rotate the inside circle until 350 degrees is under the true index as shown in Figure 44. Step 2 says to mark wind velocity up from center. The center is the grommet. Having placed the 100 arc under the grommet, simply count up the wind velocity along the given scale and make a mark. In our case, the velocity is 30 knots. Figure 44. Step 3 says to place the true course under the true index as shown in Figure 45. Notice that your wind mark is now on the right side of the scale. Step 4 says to slide the wind velocity mark to the TAS, true airspeed, line, as shown in Figure 46. Simply move the slide upward until the wind mark is on top of the 120 knot true airspeed line, or arc. You're done. All you need to do is read the ground speed and wind correction angle off the computer. See the next 2 steps. Step 5 says to read ground speed under center, the grommet. The grommet lies directly over a ground speed of 127 knots. Step 6 says to read the wind correction angle between the center line and the wind velocity mark. Your wind mark falls on the 14-degree diagonal line to the right of the scale. Your wind correction angle is 14 degrees to the right. This makes sense since the wind is from your right and slightly behind you. Let's insert our WCA and ground speed in the flight log form, Figure 47. The rest of the flight planning is a snap. Flight planning step 4. Determine the true heading. When we add the true course of 240 degrees to a right WCA of 14 degrees, we obtain a true heading of 254 degrees as shown in Figure 48. Flight Planning Step 5. Determine the magnetic heading. Correcting the true heading for variation, TVMDC, remember, gives us the magnetic heading. The variation of 4 degrees east hasn't changed on this flight. Our magnetic heading is 250 degrees. 254 degrees minus 4 degrees east equals 250 degrees. Let's insert this into our flight log form as shown in Figure 49. And now for our last step. Flight Planning Step 6. Determine the compass heading. Correcting the magnetic heading for compass deviation, TVMDC, gives us the compass heading. The compass deviation card shown in Figure 37 indicates that for a magnetic heading of 250 degrees, we'll use 240 degrees on the card since it's the closest to our magnetic heading. We should steer 3 degrees more, which gives us a compass heading of 253 degrees. 250 degrees plus 3 degrees equals 253 degrees. Let's insert this value into our flight log form as shown in Figure 50.
That wasn't too bad, was it? Believe me when I say this becomes real easy with just a little practice. Now that we know how to get to our destination, let's discuss how to obtain our expected time en route and the amount of fuel we'll use getting to where we're going. We can do this using the ground speed we've obtained during flight planning step number 3 and the front side of our flight computer. Isn't that right, Harvey?
Planning an actual flight. Let's put your knowledge to practical use and plan a short cross-country flight from Healdsburg to Nuttry Airport as shown in Figure 51. We'll assume that due to solar flares and vacuum tube shortages, all VORs in the area are inoperative, so the flight is to be conducted by dead reckoning and pilotage. This will be a simple, bare-bones flight plan. The objective is to give you a basic idea of how to make the calculations needed to put you over the destination airport. Since we're planning on making this flight within the next few hours, we'll place a call to the flight service station to obtain the weather and pertinent NOTAMs. If we were planning this flight for the following day, we would call the flight service station and obtain an Outlook briefing. Before the flight, however, we would call to obtain a standard briefing and current NOTAMs. Let's say the flight service station gave us clear skies, no applicable NOTAMs, and the following winds aloft forecast for the station nearest our area. 3,000 feet, 040 degrees at 12 knots. 6,000 feet, 070 degrees at 24 knots, temperature +1. 9,000 feet, 080 degrees at 31 knots, temperature -5. Now we're ready to draw the course line. Figure 51 shows a direct line between Healdsburg and Nuttry Airport. Whenever possible, I try to fly direct between airports. After all, that's what makes flying unique, isn't it? Unfortunately, direct flights are not always possible. Restricted areas, mountains, and large bodies of water are just a few of the things that might break up a direct flight into separate segments or legs, each having different directions and distances. Look the route over carefully and decide if a direct flight is possible or if the route should be broken down into separate legs having different directions. Cross-country planning, selecting a route. Since there is no special use airspace and there are no major obstacles on our selected route, we'll fly directly to the destination. This is convenient since it allows us to apply our wind correction to a single route. If you choose several route segments, each having different locations, wind correction must be calculated for and applied to each portion. In other words, you must work separate wind computations for each leg of the flight on your flight computer. This is where an electronic computer comes in handy. Cross-country planning, measuring the distance. After drawing the route, I like to measure the total distance. I'm concerned about whether the aeroplane has enough fuel for the flight. Having a general idea of the aeroplane's range is important here. We'll discuss a performance chart that shows the aeroplane's range under different power conditions in Chapter 15. Using the nautical mile scale on the bottom of the plotter, we find the total distance between Healdsburg and Nuttry is 46.5 nautical miles, as shown in Figure 52. Obviously, there is no range problem here. If the total distance were 400.5 nautical miles, range would be a concern, especially if you have strong headwinds and a small bladder. In that case, you might elect to land at an airport or airports along the way to obtain additional fuel. While the FARs require 30 minutes reserve during the day, 45 minutes at night, I make it a point never to be airborne with my tanks less than 1/4 full. This may be a bit conservative for some, but I've never had to turn an airplane into a glider because I ran out of fuel. Cross-country planning, selecting checkpoints. Even though our route is direct, we'll divide it up into segments. Our objective is to select visual checkpoints to aid us in navigation along the route. Yes, dead reckoning will surely point us in the proper direction of Nuttry, but monitoring checkpoints along the route allows us to make small corrections for variations in winds during the trip. Believe me when I say that winds can and do vary. I've chosen 2 checkpoints along the route, as shown in Figure 51, points A and B.
Try and pick checkpoints separated by 10 to 15 miles. You can pick more if you wish, but I don't suggest you pick fewer. Pick checkpoints you're sure are easily visible from the air. A little flying experience will quickly teach you what can and can't be seen from an altitude of 5,000 or 10,000 feet. You are about to enter another dimension. In this dimension, you will find that some shapes and colors stand out much better than others. Narrow things of neutral color, such as power lines, are hard to see and fade into the twilight zone. When selecting checkpoints, ask yourself, could I see this from a mile away on the ground? Remembering that 5,000 feet is about a mile high. You'll have some idea whether a given checkpoint is a sensible choice.
I've chosen Calistoga Airport, point A, and Moscovite Airport, point B, for our 2 checkpoints. Given the short distance of this flight, 2 checkpoints are sufficient. You don't have to choose checkpoints you will fly directly over. In fact, sometimes it's better if they are a little to the side of the flight path, preferably to the left side, since that's where you're typically seated. At night, cities or heavily traveled freeways or highways make great checkpoints, since you can't identify much else in the dark. Highways have BLS, Buick Lighting Systems. Cross-country planning, input information. Figure 53 is a typical flight log used for cross-country flight planning. I've inserted the 3 separate legs into the log along with the true course for each leg. It's the same for all legs, and distances between legs. Figure 54 shows how we measured the true course for this flight. Point A shows the line of longitude intersecting the easterly, E, plotter scale at an angle of 110 degrees. This is our true course. Point B shows a variation of 16 degrees east for our flight. Figure 55 shows the mileage for each of the 3 legs. All this information can be placed in our flight log, as shown in Figure 53. Cross-country planning. Choose an altitude for the flight. What altitude would you choose for this flight? There are several items to consider when selecting an altitude. First, if your flight takes you over mountainous terrain, plan on flying at least 2,000 feet or more above the ground. Over non-mountainous terrain, a lower altitude AGL is acceptable. If you're planning on receiving a VOR station for navigation, the higher you fly, the better the reception you'll obtain. Don't expect VOR reception for more than 25 miles if you're 1,000 feet AGL or less. Higher altitudes also mean higher true airspeeds and the possibility of favorable winds. Figure 51, point C, shows obstructions at 2,870 feet MSL. These appear to be the highest obstructions along your route. Another consideration is the hemispherical cruising altitude rule. FAR 91.159 requires that flights conducted at more than 3,000 feet AGL must be flown at odd 1,000 plus 500-foot altitudes while on a magnetic course of 0 degrees through 179 degrees. While on a magnetic course of 180 degrees through 359 degrees, you must fly even thousands plus 500-foot altitudes. From our flight log sheet in Figure 53, the magnetic course is easy to find. Simply subtract the variation. It's east, so it's least, from the true course to obtain a magnetic course of 904 degrees. Don't bother to write the magnetic course down since we only use the value to decide on cruising altitudes. We need to fly an odd 1,000-foot altitude plus 500 feet. Our choices are 3,500 feet, 5,500 feet, 7,500 feet, etc. Let's choose 5,500 feet. This will be a relatively short flight, and the time needed to climb to 7,500 feet would more than likely wipe out any small gain we might expect from an increased true airspeed. Figure 56 shows our log sheet with cruising altitudes inserted. Even though we'll be climbing to our cruise altitude from Healdsburg, we'll leave 5,500 feet in the first altitude block. Cross-country flight planning. Finding the compass heading. Finding the compass heading requires us to find the wind correction angle on our computer. To do this, we need the winds for our altitude as well as the aeroplane's true airspeed. We'll select 100 knots true airspeed for our flight. Performance charts, to be discussed in Chapter 15, allow us to determine what our true airspeed will be based on a selected power setting and atmospheric conditions. Finding the winds at our altitude requires just a bit of lower math. Referring back to our briefing, page N27, we know we have the wind direction and speed for 3,000 and 6,000 feet. Notice that the difference between the winds at 3,000 and 6,000 feet is 12 knots. Nice how that happened, eh? This means the wind velocity increases 4 knots per 1,000 feet. The winds at 4,000 feet must be 16 knots. At 5,000 feet, they must be 20 knots. Between 5,000 and 6,000 feet, the winds must be 22 knots. Additionally, wind direction changes 10 degrees per 1,000 feet. Using the same means of interpolation, you'll find the wind direction at 5,500 feet to be from 065 degrees. At 5,500 feet, the winds must be from 065 degrees at 22 knots. Now we're ready to solve a wind triangle problem on the flight computer. Figure 57 shows the wind side of the computer with steps 1 and 2 completed. Figure 58 shows steps 3 and 4 completed. Our wind correction angle is approximately 9 degrees to the left, and our ground speed, under the grommet, is approximately 83 knots. Differences between computers can easily result in a plus or minus 1 knot or plus or minus 1 degree variation. Let's fill in our flight log with the information to obtain our compass heading, as shown in Figure 59. The compass deviation card in Figure 37 shows a deviation of minus 4 degrees for a magnetic heading in the vicinity of 090 degrees. Cross-country flight planning, estimating time en route and fuel consumed. The next step in flight planning is to use our ground speed to estimate the time en route between checkpoints. If you haven't already done so, now is a good time to study Post-Flight Briefing number 14-1 to learn how to use the front side, time, speed, and distance side, of the E6B flight computer. Given a ground speed of 83 knots, we can approximate our ETE, or estimated time en route, between checkpoints. Figure 60 shows the front side of the computer with the speed reference, the kitty cat's nose, pointing to 83 knots, our ground speed. It takes approximately 12 minutes to cover the first 16.5 nautical mile leg. It takes 13 minutes to cover the next 18 nautical mile leg, and 8.5 minutes to cover the last leg. We'll round off to the closest 30-second mark. Based on an expected fuel consumption of 8.5 GPH, or gallons per hour, obtained from a performance chart you'll learn about in Chapter 15, Figure 61 shows the calculation of our fuel burn based on the time we can expect between checkpoints. We'll insert the rest of this information in our finished flight log as shown in Figure 62. The total column at the bottom of Figure 62 represents only a rough estimate of the fuel used and time required between Healdsburg and Nuttree. We haven't taken into consideration the extra fuel used in preparation for takeoff, during the climb, or the slower airspeed when climbing. These are important considerations and are even more significant as a percentage of the whole on a short flight.
Some pilots have their own formula for determining how much extra fuel they use when climbing. I've heard pilots say just add an extra 1 to 1.5 gallons of fuel for the engine start, taxi, takeoff, and climb. Frankly, this estimate is only meaningful for specific airplanes and specific conditions you're familiar with. There is a better way to find your true fuel consumption for the flight. It involves a little more work, but it's worth the extra precision you obtain in your flight planning. Let's examine a more precise method of estimating time and fuel consumption.
Figure 63 is a time, fuel, and distance to climb performance chart. You'll see this in the performance chapter, but I want to introduce it to you now. two columns are very important to us: the time to climb from sea level column and the fuel used from sea level column. At a slower climb speed of 73 knots indicated airspeed, KIAS, it takes approximately 10 minutes to climb from sea level to 5,500 feet. Since Healdsburg is at 278 feet MSL, we'll assume a sea level pressure altitude starting point. I interpolated this time by simply observing the times to climb between 5,000 and 6,000 feet. The same process yields an estimate of approximately 2.5 gallons of fuel used during this climb. With this information, you can now complete a more detailed and accurate flight log. Let's do this. A more accurate flight plan. Based on a slower climb speed of 73 knots indicated airspeed, and by the way, we'll assume indicated airspeed equals true airspeed for the climb, I know the wind will have a different drift effect on my aeroplane than it would at my cruise speed of 100 knots true airspeed. So I'll add another checkpoint to my flight log as shown in Figure 64. The additional checkpoint is called the top of climb reference. I expect to reach my cruise altitude before reaching my first visual checkpoint, so I've placed the top of climb checkpoint before Calistoga Airport. Now we must work an additional wind computer wind problem based on the slower airspeed during climb. See Figure 65. Remember, the winds are the same, only the airspeed varies. Our ground speed is 55 knots during the climb, and the wind correction angle is approximately 12 degrees to the left. This reaffirms that at slower speeds, the aeroplane must crab at a larger angle into the wind. Let's take this new WCA and ground speed and see how they apply to our flight log in Figure 64. During the climb from Healdsburg to our cruise altitude, we'll fly a compass heading of 78 degrees, as shown on the first line of Figure 64. What we need to know is how much distance we'll cover in 10 minutes, the time our chart showed was required to climb to 5,500 feet. This is the distance to be placed in position A. We can figure this out by using our computer to determine how much distance we cover in 10 minutes at 55 knots, as shown in Figure 66. It looks like we'll cover approximately 9 miles during the climb. We'll put this value in position A of our flight log. Since the distance to Calistoga from Healdsburg is 16.5 miles, this means that 7.5 miles is left to fly at cruise airspeed, position B. The next calculation is how much time it takes to cover 7.5 nautical miles at 83 knots, the rest of the distance to our first visual checkpoint, Calistoga. Figure 67 shows that it takes approximately 5.5 minutes to cover 7.5 miles at 83 knots. We'll put this information in position C of our flight plan. The last item we must determine is how much fuel we used during the 5.5-minute cruise segment when we're consuming fuel at a previously determined rate of 8.5 GPH. Figure 68 shows that 0.78 gallons are used for this 5.5-minute segment. We'll put this information in position D of our flight log. Our completed flight log is shown in Figure 69. Note the small note I've added at the bottom right of the flight log. It says that note number 1 of the performance chart in Figure 63 states we should add 1.4 gallons of fuel for engine start, taxi, and takeoff. A total flight time of approximately 37 minutes and fuel consumption of approximately 7.68 gallons is estimated for this flight.
Now, folks, this is true. It's a good idea to compare the fuel estimate against what really happens in order to see how well the process is working, and whether any of the fixed amounts you're using, such as the rate of fuel burn at cruise or the amount of fuel for startup, taxi, and takeoff, need to be adjusted. Keep in mind that any such numbers are averages, and your number may vary as much as the fuel prices.
While it would be nice to think everything can be measured with great precision, the fact of the matter is your fuel burn will not be accurate to the tenth of a gallon. In fact, there can be several gallons variation in your estimation of fuel on board, based on the size of the fuel tanks and how close to the top the line person, the petroleum molecule fluid allocation person, fills them up. It pays, however, to plan as precisely as possible while keeping real-world considerations in mind. Do not ever try and stretch your flight based on the fact that by a paper calculation, you should have a few gallons of fuel left. Always be aware of the imprecision of these seemingly precise calculations and fly conservatively in the twilight zone.
Now, folks, flight planning can be a lot of fun, but I don't want you to think it must be this detailed for short flights. If I'm headed to a local airport 10 miles away that I'm very familiar with, I check the weather and the NOTAMs, pre-flight the plane, and make sure I have full fuel and go. It's that simple. It's reasonable to say that the farther away from the airport you fly, the more detailed the flight planning is necessary. Make no mistake about it, even experienced pilots who slack off on their flight planning get to fly gliders, airplanes with fuel-exhausted engines.
Final words on electronic flight computers. An explanation on the use of the electronic flight computers hasn't been included for a very good reason. They're easy to use. Many of these wonderful little devices are menu-driven, making it unbelievably easy to solve wind, time, distance, and fuel problems. We worked on the mechanical computer so you would know the principles. With that in hand and in mind, you can feel more confident in the use of an electronic computer, where it's easy to crunch numbers without understanding what they mean. I am all for technology, but only if you understand what it's doing for you. Quite frankly, I am simply amazed at all the wonderful little devices available for people nowadays. A friend's grandfather purchased a $1,200 hearing aid. He claims it has call waiting. Post-flight briefing number 14-1. The mechanical flight computer. Figure 70 shows the most common mechanical flight computer in use today. It's often referred to as the E6B computer, and is a device you should become familiar with. Patented by Lieutenant Philip Dalton on June 30, 1936, the E6B has become one of the most familiar items in all of aviation. E6B was probably a military designation. You might be wondering why I recommend learning to use a mechanical flight computer when there are so many wonderful electronic computers on the market. There are two reasons. First, it's important that you understand the principles behind the calculations, and the E6B shows the facts in a way electronic computers can't. Second, you can always get a usable calculation from an E6B. No dead batteries, bad circuit boards, inoperative LCDs, or other electronic maladies. Putting on a happy face. The E6B does not, at first glance, present a friendly face, figure 70. Numbers upon numbers, scales upon scales, windows within windows. Any of these could cause your blood pressure to rise so fast that if it weren't in your skin, you'd be a fountain. It's even created mental vapor lock in some students, whose heads spin so fast after one look that they feel like a termite in a yo-yo. It would do little good for me to say, "Don't worry, it will all make sense to you soon." So let me do something better. Figure 71 shows a simplified version of this computer.
Rod has taken out all the confusing items on the computer's face, leaving just the basics. You are welcome to photocopy this figure, cut out the white internal ring and paste it, with removable paste, over the internal movable ring of your computer. You may have to expand or shrink the photocopy to make it fit. After a short time, practicing with this cleaned up, movable inner ring, you can pull it off and the original computer's complexity won't be so overwhelming. Caution! Only use this photocopy to become familiar with the face of the computer. It's not meant for use outside of post-flight briefing number 14-1. Many important items have been removed.
Another option is to make a photocopy of Figure 71, carefully cut the white inner ring from the black outside ring, and construct a temporary paper computer to practice with as shown in Figure 72. Either way, this cleaned-up computer is much easier and more enjoyable to use during the learning process. Dance of the decimals, the number scale. In Figure 71, the inner, white and movable, ring is matched up against the outer, fixed ring. The numbers on both scales match one another. Find the number 10 on the very top of the computer's inner or outer ring. Moving clockwise around both scales, the numbers increase in value. To the right of 10 is 11, 12, 13, and so on, all the way to a value of 90, which is a full digit left of 10. These numbers can represent any value you want. We could let the number 10 equal 100. Then the digits to the right would be 110, 120, 130, and so on. Or we could let 10 equal the value of 1.0. The number to the right would then be 1.1, 1.2, 1.3, and so on. It's very important that you stay with the same numerical category of values you start with when solving a computer problem. In other words, ones, tens, or 100s. If you are letting the value of 10 on the scale equal 100, don't let the value of 11 equal 1.1. It should represent a value of 110. Miles on the menu, converting nautical and statute miles.
Lock the firing solution into the computer. Do not open the outdoors.
Captain, there are still miles on the menu.
Two forms of distance measuring are used in aviation: nautical miles and statute miles. Statute miles are normally used for measurement of visibility, while nautical miles are more often used in navigational computations. You will generally find most airspeed indicators on newer airplanes using knots, nautical miles per hour, instead of statute miles per hour. But there will be situations where it is necessary to convert from one type of mile to the other. Now, where was I? Any surface contacts, Mr. Bardon? Any sonar contacts, Mr. Kamarov?
A nautical mile is a distance of 6,076.1 feet. A statute mile is a distance of 5,280 feet. The conversion factor is 1.15. In other words, a nautical mile is equal to 1.15 statute miles. Another way of saying this is that one nautical mile is longer than a statute mile. To convert nautical miles to statute miles, simply multiply it by 1.15. For example, 20 nautical miles equals a distance of 23 statute miles. 20 times 1.15 equals 23. To convert statute miles to nautical miles, simply divide the statute mile value by 1.15. 23 statute miles divided by 1.15 equals 20 nautical miles. Here's how to remember the difference between nautical and statute miles. Think of two ropes that appear to be equal in length. One rope, however, has a knot in it, as shown in Figure 73. If we let the length of the rope without the knot equal a value of 1, then the knotted rope also appears to be the same length. But when the rope with a knot in it is unraveled, it's actually longer than the other rope, 1.15 times longer. This makes sense, since a nautical mile is 1.15 times longer than a statute mile. So, when you compare equal values of nautical and statute miles, remember that the value with the knot, nautical, in it is actually longer or bigger. There is an easy way to convert nautical and statute miles using the E6B computer. On the computer's outside ring, there is a conversion arc, Figure 74. Simply put the mileage value you want to convert under the stat or not arrow on the inside ring. Then follow the arc across and read the equivalent mileage value on the same inside ring. In Figure 74, a value of 6.6 nautical miles is set on the inside ring under the NAUT arrow. The STAT arrow points to 7.6 as the statute mile equivalent value. Let's convert 90 nautical miles to statute miles. Figure 75 shows this conversion. Place 90 under the NAUT arrow on the inside ring and read the statute mile value under the STAT arrow on the same ring. 90 nautical miles equals 103.5 statute miles. I, or the FAA on a test, might ask you to convert 103.5 statute miles to nautical miles. You would place 103.5 under the STAT arrow and read the nautical value of 90 miles under the NAUT arrow. Be careful when reading numerical values on the computer's inside or outside ring when marks instead of actual digits are used to represent the scale's values. For instance, in Figure 76, between 250 and 300 on the inside ring, there's just not enough space to place whole number values. In other words, 26, 27, 28, and 29. These whole number values are represented by longer slashed lines. Between each longer slashed line are smaller lines representing an increase in value of 0.2, 2, or 20. As you can see, point A represents either 0.254, 25.4, or 254, depending on the original value we started with. Try converting 276 statute miles to nautical miles. Figure 77 shows this process. Placing 276 under the STAT arrow gives you 240 nautical miles. Of course, if the statute mile value was 27.6, then the nautical value would be 24. Remember to keep with the same value of ones, tens, or 100s. In other words, 27.6 statute miles wouldn't be 240 nautical miles. This is part of the common sense needed when solving these problems. At the bottom of your plotter is a mileage scale, as shown in Figure 78. Both statute and nautical mileage scales are available for easy use. if you don't have your flight computer with you and you can't remember how to convert nautical and statute miles, you can easily do it on the matched scales at the bottom of the plotter. Simply find the statute mile value on the plotter's statute scale and move to the opposite nautical scale to read the nautical mile value. It doesn't get any easier than that. Time, distance, and speed computations. Computing time, speed, and distance is a necessary skill for all pilots. After all, how can you estimate the fuel you use if you don't know how long it will take you to get somewhere? The following formula should be committed to memory. Speed equals distance divided by time. This formula states that your speed is the ratio of the distance traveled over the amount of time it takes to travel that distance. If you have any two of these three items in the formula above, either speed, time, or distance, you can determine the third. For instance, if you know how much distance you traveled in a certain amount of time, you can determine your ground speed. If you know your ground speed, you can tell how much time it will take to travel a certain distance, or you can tell how much distance you will travel in a certain period of time. Think about this carefully. We always measure our speed in either miles per hour or knots, which is nautical miles per hour. If you're doing 60 miles per hour, you'll travel 60 miles in 1 hour. That's 1 mile per minute, since there are 60 minutes in 1 hour. At 120 miles per hour, you'll travel 2 miles per minute. These are handy numbers to keep in mind. Whenever the word per is used in arithmetic, as in miles per hour or nautical miles per hour, it represents some sort of ratio. If I went 120 miles per hour, it means I traveled 120 miles in 60 minutes. Such a ratio is represented as 120 miles divided by 60 minutes in an hour equals 120 miles per hour. Your computer is nothing more than a mechanical device for picturing a ratio. You're going to be amazed how easy this little device is once you understand how ratios are shown on the computer's face. For example, set up your computer as shown in Figure 79. From now on, we'll refer to the white, movable ring as the inside scale and the fixed outer ring as the outside scale.
Which scale of the computer has the greatest distance around it? Yes, the outside scale has a larger circumference, thus the greatest distance. All distance values will be found on the outside scale. That's a memory aid. Distance refers to the outside scale, and this is where you look to find any distance values. What do the hands of a clock do? Yes, of course, they tell time, but they also move. Which scale of the computer moves? The inside scale moves. As a memory aid, the inside scale of your computer is where you'll find all your time values. Any value other than time, such as distances, will be shown on the outside scale.
Notice there is a blackened triangle on the inside scale that looks like a kitty cat's nose in Figure 79. This is the hour index, since it represents a time value of 60 minutes in an hour. From now on, we'll call the hour index the kitty cat's or cat's nose. With the cat's nose, the hour index, pointing to 120, we've set up a ratio. What we're saying here is that we went 120 miles, distance on the outside scale, in 60 minutes, time on the inside scale. Many similar ratios can be shown on the computer's face. For instance, we know intuitively that at 120 miles per hour, we will travel 60 miles in half an hour. Find the 30-minute mark on the inside scale, the time, in Figure 80. Opposite the 30-minute mark, you'll find 60 miles on the outside scale, distance, as shown by position A. Position B shows a ratio of 16 miles per 8 minutes. Position C shows a ratio of 24 miles per 12 minutes. And position D shows a ratio of 40 miles per 20 minutes. All these ratios represent a speed of 120 miles per hour. If you have any two of the three variables in speed, time, or distance, you can find the other on the computer's face. One last thing before we start solving problems. What do kitty cats do? I hope you said they PER. No, that's not a typo. I meant purr. Now, this is not the purr we're familiar with, but it sounds the same, doesn't it? As a memory aid, we'll say that the kitty cat's nose always points to the PER or purr value you're working with. In other words, it points to miles per hour, nautical miles per hour, or, as you'll soon see, gallons per hour. Remember, you'll always be working with some PER or purr value when doing speed, time, and distance computations. Now you know where to find speed, time, or distance variables. Time is on the inside scale, distance is on the outside scale, and speed, per quantities, is on the top of the cat's nose. These ratios are shown in the center of the computer. For your reference, Figure 80.
I like using these types of symbols to solve problems as long as they make sense. Several years ago in a Mexican restaurant, the restroom doors read Matador and Bull. Now those are confusing symbols. I didn't know what to do. Fortunately, the cat's nose is a lot simpler to use. Let's solve some problems.
Problem 1. If your speed is 105 miles per hour, how much distance will your airplane cover in 20 minutes? To solve this problem, ask yourself which of the three variables, speed, time, distance, you have and which one you are looking for. You have speed and the time. What you want is the distance. First, point the cat's nose at the purr value of 105 miles per hour, as shown in Figure 81. Since time is always found on the inside scale, find 20 minutes on the inside scale. Opposite the time, you see a value of 35 on the outside scale. You'll cover 35 statute miles in 20 minutes at 105 miles per hour. You can also say that at 105 knots you will cover 35 nautical miles in 20 minutes. Once you find an answer, you must always make certain it makes sense. Since at 120 miles per hour you travel 2 miles per minute, at 105 miles per hour, close to 120 miles per hour for an estimate, you should have a time-distance value somewhere near 2 to 1. A value of 35 miles in 20 minutes is close enough to confirm your numbers are accurate. After all, if you arrived at an answer of 350 miles, you know this wouldn't be correct unless you were captain of the Starship Enterprise. Problem 2. If we travel 7 miles in 4 minutes, what is our speed? The value you're looking for is the purr value, and it will be found on top of the cat's nose, on the outer scale, as shown in Figure 82. Simply set 7 miles, distance, on the outside scale over 4 minutes time on the inside scale, and read what the cat's nose, per index, points to. Your speed, according to figure 82, is 105 miles per hour, which is the same speed as our previous problem. Problem 3. At 138 miles per hour, how long will it take to travel 81 miles? First, what does common sense tell you about the answer? Obviously, it will take you less than 1 hour or 60 minutes. Correct? After all, in 1 hour at 138 miles per hour, you'd travel 138 miles. The value you're looking for is located on the inside time scale. Figure 83 depicts this problem. Set the cat's nose, the per index, to 138. On the outer distance scale, you'll find 81 miles, and underneath that value, you'll find a time of 35 minutes. Of course, it's possible to interpret this as either 3.5 minutes or 350 minutes, but neither of these alternatives makes sense. Problem 4. At 90 knots, how much distance will you cover in 15 minutes? By now you know that the value you're looking for, distance, is on the outside scale. Set the cat's nose, the per index, to 90, and read the distance value on the outside scale over the 15-minute time mark on the inside scale as shown in figure 84. You obtain a value of 22.5 miles. This makes sense in that 60 knots is 1 mile per minute and 120 knots is 2 miles per minute, so 90 knots should be somewhere in between, or 1.5 miles per minute. At 15 minutes, you should travel 1.5 times this amount, or 22.5 nautical miles. Problem 5. What is your ground speed if you traveled 13 nautical miles in 10 minutes? Figure 85 shows how this answer is derived. Rotating the inside time scale so 10 minutes is underneath the distance of 13 miles on the outer distance scale leaves you with the cat's nose, the per index, pointing to a ground speed of 78 knots. I might have also asked what the ground speed is if you traveled 130 nautical miles in 1 hour and 40 minutes. Directly under the 10-minute mark is the 1:40 mark. Since 1 hour and 40 is 100 minutes, you could set this time directly under 130 nautical miles, giving you a ground speed of 78 knots. Problem 6. What distance will you cover in 9 minutes at a ground speed of 172 knots? Figure 86 shows how this answer is derived. Setting the cat's nose, the per index, to 172, and locating 9 minutes on the inside time scale, gives you a value of 26 miles on the outside distance scale. Of course, this can't be 2.6 miles, nor can it be 260 miles. Your answers must always make sense. Problem 7. How much time will it take to travel 25 nautical miles if your ground speed is 158 knots? Figure 87 shows how this answer is derived. Set the cat's nose, the per index, to 158 and find 25 miles on the outside distance scale. Underneath it is a time value of 9.5 15.5 minutes. Fuel consumption problems.
Now, folks, finding fuel consumed is very similar to finding speed, time, and distance on the computer. The per value with fuel consumption is gallons per hour. Instead of distance on the outside scale, you'll find the fuel consumed. Of course, time is always found on the inside scale. Now let's work a few problems.
Fuel problem 1. If your fuel consumption is 9 gallons per hour, how much fuel will the airplane consume in 1 hour and 30 minutes? You don't even need a computer for this one, do you? First, set the cat's nose to the per quantity as shown in Figure 88. The amount of fuel burned will be on the outside scale, directly above the time value on the inside scale. 90 minutes or 1:30. In 1 hour and 30 minutes, you'll use 13.5 gallons of fuel. Fuel problem 2. If your aeroplane consumed 21 gallons of fuel in 2 hours and 30 minutes, 2:30, what was your rate of fuel consumption? We are looking for the per or gallons per hour value, which will be found on top of the cat's nose. Set 21 gallons on the outside scale, fuel burned, over 150 minutes, or 2:30, on the inside time scale, as shown in Figure 89. The cat's nose, the per index, points to 8.4 gallons per hour fuel consumption rate. Fuel problem 3. With a fuel consumption rate of 15.6 gallons per hour, how long can you fly with 90 gallons of fuel on board? Common sense tells you the answer is going to be somewhere around 6 hours. Set the cat's nose, the per index, to 15.6 as shown in Figure 90. Finding 90 gallons on the outside scale for fuel burned gives you a time value of approximately 345 minutes. Read the time scale carefully. You could divide 345 minutes by 60 to obtain the hours flyable, or you could look underneath the minutes scale to find the hours scale. The hours scale is simply easier to use when dealing with large minute values. Post-flight briefing number 14-2. Finding density altitude, true airspeed, and your true altitude. Finding density altitude. You can use the computer to find density altitude if you have two variables, the pressure altitude and the outside air temperature. Figure 91 shows a density altitude computation scale on a typical flight computer. If you set the outside air temperature on scale A, opposite the pressure altitude on scale B, you can read the density altitude at the window located on scale C. This is a handy way to easily compute density altitude without using a fine-lined graph. In Figure 91, the outside air temperature at sea level pressure altitude is 15 degrees Celsius, which is standard temperature at sea level. Under these conditions, pressure altitude is equal to density altitude. A sea level or zero density altitude value is shown at the window located on scale C. With an outside air temperature of plus 10 degrees Celsius at a pressure altitude of 10,000 feet, what is the density altitude? Sliding the plus 10 degrees Celsius over a 10,000 foot pressure altitude in Figure 92, you see that your density altitude is 11,700 feet. Finding true airspeed. Using the same procedure for finding density altitude, you can easily find your true airspeed on the face of the flight computer. Figure 93 shows your computer with an outside air temperature of minus 12 degrees Celsius with a pressure altitude of 5,000 feet, scale A. The true airspeed, TAS, is read on the outside scale opposite the calibrated airspeed, CAS, on the inside scale. We'll use indicated airspeed, IAS, in lieu of calibrated airspeed since they are not that much different at cruised airspeeds. An IAS of 150 knots produces a TAS of 156 knots, as shown by position B. Suppose your indicated airspeed is 125 knots. What is your true airspeed under the same condition? Position C shows an indicated airspeed, same as calibrated airspeed for our purposes, of 125 knots on the inside scale, giving you 130 knots true airspeed on the outside scale. Finding your true altitude.
In the chapter on flight instruments, we discussed true altitude. Altimeters read our height above sea level when they are corrected for non-standard pressure and temperature. Typically, however, we don't correct the altimeter for variations in temperature since these variations aren't normally that large. Not like the croc I hunted yesterday, she was a beauty. Nevertheless, under certain conditions, temperature can cause a rather large error. Let's do a true altitude computation on the computer. Here are the conditions. 1. Your aircraft is flying at an indicated altitude of 10,500 feet. 2. The altimeter setting is 30.42 inches of mercury. 3. The outside air temperature is minus 25 degrees Celsius. Crikey, that's cold.
What is your true altitude? Step 1. Find your pressure altitude. To find the pressure altitude, the altimeter must be set to 29.92 inches of mercury and the face of the altimeter red. In other words, the indicated altitude red. Since we don't have an altimeter knob to twist, we'll use our previous knowledge of how the altimeter works to determine pressure altitude. Moving the numbers down from 30.42 inches to 29.92 inches is a change of 0.5 inch of mercury. This means the hands move down 500 feet, and the pressure altitude is 10,000 feet. Step 2. Place the pressure altitude under the temperature in the computer's altitude computation window, the window on the left side of the E6B's face. Figure 94, position A, shows the temperature of minus 25 degrees Celsius placed over a pressure altitude of 10,000 feet. Step 3. Read the true altitude over the indicated altitude on the inside scale. We'll assume that indicated altitude is the same as calibrated altitude for all these examples. See glossary for definition of CAL-ALT, calibrated altitude. Figure 94, position B, points between the circled abbreviations for true altitude, TRUE, ALT, on the outside scale and calibrated altitude, CAL-ALT, on the inside scale. We'll use the indicated altitude instead of calibrated altitude. Finding 10,500 feet indicated altitude on the inside scale at position C, we see that our true altitude is 9,700 feet, as shown directly opposite the outside scale. Under large differences in pressure and temperature from standard, it's not unusual for indicated altitude to differ substantially from true altitude. Under these extreme conditions, you should consider flying a little higher than normal on your cross-country flights if you're planning on being close to terrain. This caveat is especially true for night flight. There are many more things your computer can do for you. They are beyond the scope of this book, but I would recommend that you purchase a mechanical flight computer and study its manual. You're going to be surprised at how versatile this simple little machine really is. Post-flight briefing number 14-3. Creating a wind triangle. Let's construct a wind triangle for the flight from Table Rock to AVA Martin Memorial, shown in Figure 95. Our true airspeed is 100 knots, as determined by the aeroplane's performance charts, and the wind is from 020 degrees at 40 knots, as given by the flight service station. The true course along our route is 60 degrees. Let's use a wind triangle to determine our expected ground speed and wind correction angle for this flight. Step 1. The first step in construction of a wind triangle is to draw a line between the departure and destination airports on the sectional chart as shown in Figure 95. Step 2. Next, we want to visually represent the wind with a line of specific length and direction. The wind is from 020 degrees at 40 knots. Winds given by the flight service station are angled with respect to the true North Pole. In other words, they are always in a true direction. Simply draw a line angled at 20 degrees to true north, running through the destination airport, as shown in Figure 95, point B. Figure 96 helps you understand how to draw a line at this angle. This line represents the wind direction. What we need to do now is find some way of representing the wind's velocity with this line. The easiest way is to let the line's length represent the wind's speed. Let's arbitrarily make 1 inch equal to 10 knots of wind. We could use any value we desire. This is simply a personal choice for this example. Since our wind velocity is 40 knots, make the line 4 inches long. 4 times 1 inch. I like to mark outward of the line in 1 inch intervals starting at the center of the airport, as shown in Figure 95. From this picture, you can easily see the wind is a headwind blowing from your left. This single picture already allows you to visualize that your ground speed will be slower than your airspeed, and you'll have a left wind correction angle. Step 3. Since we've represented the wind's direction and velocity by a line of a specific length pointed in a specific direction, we need to do the same with the aeroplane's speed and direction. The final step requires you to take the ruler, put one end up against the tail of the wind line as shown in Figure 97, position A. Next, count outward along the ruler to a value of your true airspeed, or 100 knots. Since we've already agreed that 1 inch equals 10 knots, measure outward 10 inches. 10 times 1 inch equals 10 inches, as shown by point B on the ruler. Finally, pivot the ruler about point A until the true airspeed dot, point B on the ruler, is in contact with the course line at position C. Draw a line from C to the tail of the wind arrow at point A. You're done. That's it. You've got yourself a completed wind triangle depicted by points C, A, and AVA Martin Airport, as shown in Figure 98. The angle between the true airspeed line, position C to position A, and the course line, position C to AVA Martin, is our wind correction angle of 15 degrees. This represents how much the nose of the aeroplane must point to the left of the course to allow you to track directly along the selected course line from Table Rock to AVA Martin. In other words, the nose must be pointed 15 degrees to the left of a true course of 060 degrees. You must head 045 degrees, in other words 60 degrees minus 15 degrees equaling 45 degrees, to fly parallel to the line drawn from Table Rock to AVA Martin Airport.
The length of the line in inches from position C to AVA/Martin is the ground speed you can expect. Measuring this distance as shown in Figure 98 gives you 6.6 inches. At 10 knots per inch increment, this equates to approximately 66 knots ground speed. Now folks, this is true. And Figure 99 shows the comparison between the completed wind triangle and the wind triangle made by the mechanical flight computer. Notice the similarity. Next time you use the mechanical flight computer, realize that you're still creating a wind triangle.
Final words on wind computations. Is it necessary to hand-draw a wind triangle before every flight? Absolutely not. It is necessary to use a slide type or electronic computer to help determine the effect of wind on your airplane. Yes, I believe it is. You need to know how the wind will affect your fuel consumption and time en route. This means some sort of wind computation is necessary. Chapter 15. Aeroplane Performance. Know before you go. Cessna 2132 Bravo, this is Departure Control. Please squawk standby. There's a problem with your transponder, said the controller. What's the problem? Asked the pilot of the Cessna 152. Well, we show your airplane climbing through 19,500 feet, doing 320 knots, replied the controller. The quick-thinking pilot with an excellent sense of humor replied, Oh no, that's right. We just had our engine overhauled. Now that's real performance, except of course that it was unreal performance. The controller could easily predict that no 152 on or off the Earth was capable of doing 320 knots or climbing to 19,500 feet.
Airplane performance is predictable. Unlike psychics, pilots don't need crystal balls or Ouija boards to make performance estimates that are very close to the mark. An airplane's takeoff, climb, cruise, and landing performance is easily estimated from a variety of charts found in the pilot's operating handbook, which is as much a part of the aircraft's equipment as the wings. If you don't see either the wings or the pilot's operating handbook, better ask about it. Your job is to know how to use the performance charts. As you'll soon see, all airplane performance is based on one very important item: air density. That's because the thickness of the air flowing over the wings or into the engine determines how well the airplane performs or fails to perform.
Air density. Aeroplanes are remarkably similar to people in that both experience decreased performance in less dense air. Anyone who's ever hiked to the top of a high mountain knows how human performance decreases. One trip up El Capitan at Yosemite, and you feel like you're the big bad wolf, huffing and puffing, as though you were trying to blow a house down. Aeroplanes, too, are air-breathing machines, and they respond much as you do to lowered air density. The more air molecules flowing over the aeroplane's wing, the greater the lift developed. Anything that thins the air reduces the wing's ability to generate lift. Aeroplane engine performance is affected in the same way. Power plants require air to run. Anything reducing the amount of air the engine swallows diminishes its power output. Less power equals less performance. No fancy mathematics here. It's really quite simple. To fly without understanding this important relationship is about as wise as having the three little pigs invite the wolf in for a spot of tea, which would certainly give new meaning to the term pig out. Let's take a closer look at the things which affect aeroplane performance. Height. As we discussed in an earlier chapter, the higher you go, the less frequently you or your aeroplane's wing will run into air molecules because they are fewer and farther between with increasing altitude. This is another way of saying that the air density is less. Fewer air molecules are available to move past the wing, so lift is reduced and performance is decreased. Expect higher altitudes to provide you with slower acceleration, longer ground runs, and shallower climb profiles, as shown in Figure 1. Heat. Heat is also notorious for reducing performance of aeroplanes. Heated air is much less dense than colder air. Expect slower acceleration, longer takeoff runs, and shallower climb profiles on hot days, as shown in Figure 2. Humidity.
High humidity also reduces airplane performance by thinning the air. Wait a minute, you say? How can adding moisture to air make it thinner? Moist air is lighter, thus less dense, because water molecules are actually lighter than air molecules. Mind you, I said water molecules, not water, which is obviously a lot heavier because of the density. Well, shoot, if you've ever tried to carry a bucket of steam, it rises because it's lighter than air. You've had direct proof that moist air is less dense than dry air. By itself, moist air isn't much of a problem. This is why most performance charts make no correction for humidity. Nevertheless, in combination with heat and height, it could put your airplane dangerously close to those trees at the end of the runway. The very best way to think of all of this is to remember that you should avoid joining the aviation's 4-H club. Because if you have height, heat, and humidity, you have heck to pay. Shoot, those 4-H's. Any one or a combination of these factors can turn an airplane into a car by keeping it from becoming airborne. If you want to avoid ending up on the Oprah Winfrey Show, don't do weird, strange things in your airplane, like taking off with a lot of height, heat, and humidity. I hear you're saying, how much is a lot? Good question. The effects of height and heat are all combined into one very important calculation called density altitude.
Density altitude. Taking off at an airport near sea level usually results in good acceleration and climb performance. The elevation has no effect on performance. Temperatures are usually moderate, and the humidity is generally not too high. If we take off from an airport situated at 100 feet MSL, the aeroplane performs quite well. Suppose, however, that it's an extraordinarily hot day at our 100-foot MSL airport. Will the airplane perform well? No. Because of the high heat, the air might have a density equivalent to an altitude around 3,000 feet. The term density-altitude describes how dense the air feels to the airplane, regardless of the airplane's present height above sea level. Density-altitude is an extremely important term for you to understand. For example, even though the airplane was physically at 100 feet MSL, in terms of airplane performance, the airport has a density-altitude of 3,000 feet. In Chapter 5, I mentioned that pressure altitude was the reference to which airplane engineers calibrate their performance charts. Pressure altitude is what the altimeter indicates when 29.902 inches of mercury is set in the altimeter's Kollsman window. In addition to the pressure altitude reference, engineers also calibrate many of their performance charts to a standard temperature of 59 degrees Fahrenheit, otherwise known as 15 degrees C, at sea level. Engineers call the conditions of 29.902 inches of mercury and 59 degrees Fahrenheit, 15 degrees C, at sea level standard conditions. Since you must have a starting point or reference when calibrating the performance of airplanes and their instruments, standard conditions at sea level is a good starting place. For example, when you ask the teacher how your son Bobby is doing in school, he or she normally compares his performance to that of a previous year. The teacher might say, "Well, compared to last year, Bobby is doing better." If the teacher said, "Well, in reference to all forms of animal and plant life on this planet, little Bobby is holding his own against most species of protozoa," then Bobby is in trouble. Standard temperature and pressure conditions are simply a reference point where a baseline of performance is established. Of course, if standard conditions existed at sea level all the time, we wouldn't have to worry about changes in air density and its effects on airplane performance. Unfortunately, Mother Nature doesn't like constant, standard conditions. Let's assume you're at an airport at 4,000 feet MSL and standard conditions exist at sea level. Let's also assume that temperatures decrease at 3.5 degrees Fahrenheit, or 2 degrees C, per 1,000 feet. By now you know that while this is the engineer's standard lapse rate and is used for instrument calibration, it is seldom the actual lapse rate found in the environment. Under these conditions, the temperature at 4,000 feet should be 45 degrees Fahrenheit. 4 times 3.5 equaling 14, and 59 minus 14 equaling 45 degrees Fahrenheit. Suppose it's really hot, say 100 degrees Fahrenheit or 38 degrees C, at 4,000 feet. This is definitely a non-standard temperature. Is the airplane going to perform like it normally would at 4,000 feet? Definitely not. In fact, the airplane is going to perform more like it's at 7,500 feet. I'll show you in just a moment how I arrived at this value. Because of the higher than normal temperature, the air has a density altitude, a performance altitude, if you want to think of it that way, of approximately 7,500 feet. Think of density altitude like you do personal debt. Whenever debt increases, bad things happen. When debt decreases, good things happen. Increasing density altitude decreases airplane performance. Decreasing density altitude increases airplane performance. Density altitude example number 1. Finding the density altitude is easy with the density altitude chart in Figure 3. Along the bottom horizontal axis is a temperature scale with Fahrenheit and Celsius markings. Rising diagonally upward from left to right are pressure altitude lines. On the left side of the chart is the density altitude reading along the vertical scale. If you know the pressure altitude and the air temperature for your location, you can easily find the density altitude. Let's see how this works. Assume your outside air temperature, OAT, is 80 degrees Fahrenheit, 27 degrees C, and the pressure altitude is 7,000 feet. Referring to Figure 3, find 80 degrees Fahrenheit, 27 degrees C, on the bottom horizontal scale and move upwards until reaching the 7,000-foot diagonal pressure altitude line. Make a mark at this point, position 1, and move horizontally to the left. The number on the left vertical scale is the density altitude. In our example, the density altitude is 10,000 feet. Density altitude example number 2. What is your density altitude if the pressure altitude is 3,257 feet and the OAT is 75 degrees Fahrenheit, 24 degrees C? First, you must locate your pressure altitude between the diagonal lines on the density altitude chart in Figure 4. Locating the pressure altitude value of 3,257 is easy if you draw the intermediate values between the 1,000-foot pressure altitude lines. Simply draw the 3,500-foot pressure altitude value between the 3,000 and 4,000-foot pressure altitude lines as shown in Figure 4. Now, draw an intermediate value between the 3,000 and 3,500-foot pressure altitude line. This will represent the 3,250-foot pressure altitude value. Move up the 75 degree Fahrenheit, 24 degrees C line until reaching the pressure altitude line of 3,250, as shown by position 2. This is very close to the actual pressure altitude value of 3,257 feet. Go across to the left to find a density altitude value of approximately 5,000 feet.
Now, folks, at the end of this chapter, in post-flight briefing number 15-1, Rod's included 2 different types of density altitude problems that show up on the FAA knowledge exams. Unfortunately, one of the problems is more test-oriented than it is practical in the real world. Now, don't ask me why test creators do this. It reminds me of some 8th century monk scribe inserting words in an ancient text that eventually becomes the foundation of our modern English language. As the monk is writing the official word for sharp instrument with a handle that cuts your steak, he looks around, then mischievously inserts a K in the word knife. No one knows why he did this, but it's a done deed, and we've got to live with it. Study post-flight briefing number 15-1 carefully during your final preparation for the knowledge exam.
Let's look at an even more meaningful example of how density altitude relates to airplane performance. Before we can do that, we need to understand something known as service ceiling. Service ceiling. Most POHs, pilot operating handbooks, for individual airplanes inform pilots of the maximum height the airplane can be flown to before it ceases climbing. Technically, the altitude at which the climb rate drops to less than 100 feet per minute. This height is known as the service ceiling, Figure 5. The service ceiling applies to a brand new airplane with a new engine. You can expect older airplanes to have service ceilings less than the book value. Figure 6 shows 14,700 feet as the service ceiling of a 1980 Cessna 152. Of course, if the density altitude is close to or equal to that of the 14,700-foot service ceiling, the airplane will only climb at 100 feet per minute or less. Density altitude problem number 3. Suppose you're flying a new Cessna 152 from an airport where the pressure altitude is 10,000 feet, and the OAT is 905 degrees Fahrenheit, 35 degrees C. That's hot for an airport that high. Better be careful. What is the density altitude at that airport? Use the density altitude chart, Figure 4, to identify where the 95 degree Fahrenheit or 35 degrees C line intersects the 10,000 foot pressure altitude line in position 3. Moving horizontally to the left, you determine the density altitude to be 14,700 feet. How will your aeroplane perform? Not well. Better get out your driver's license, since driving is what you'll be doing. The airplane, if it gets off the runway at all, will barely climb 100 feet per minute.
Well, shoot, you're going to scare quite a few people standing at the end of the runway. Take Rod's word for it. If it's an older airplane, you'll never become airborne under the conditions in this example. And if it's a tired old airplane, you'll notice something's wrong when it'll take full power to taxi. That's a joke. But it does emphasize how much the performance decreases.
Here's Machado's service ceiling caveat. Never count on more than 75% of an aeroplane's posted service ceiling. This is admittedly a conservative estimate if the aeroplane is new, but a wise and realistic one if the aeroplane is old. By my numbers, I would expect a Cessna 152 to climb no faster than 100 feet per minute at a density altitude of 11,025 feet, 75% of 14,700 feet. Anything that makes the air thinner, lower pressure, high heat, high humidity, increases the density altitude. Anything making the air thicker, increasing pressure, low heat, and low humidity, for example, decreases the density altitude. Machado's Whammo density predictor states, for a given pressure altitude, the density altitude increases by 1,000 feet for every 15 degrees Fahrenheit, 8.5 degrees C, of temperature increase. Given this, and knowledge of your airplane's service ceiling, you can easily estimate the amount your airplane's performance will decrease. Performance charts. A local passenger who was afraid to fly on airliners once asked a mathematician odds maker what the odds were of a bomb being on an airplane. "Oh, about 1,000,000 to 1, said the mathematician. "It's very unlikely that would happen." Several days later, the same nervous passenger called the mathematician and asked, "What are the odds of 2 bombs being on the same airplane?" The mathematician mentally calculated the answer, then replied, "Oh, approximately 65 million to 1 against it. There's no way you're going to have 2 bombs on an airplane." Several months later, the mathematician met the nervous passenger and asked if he felt better about flying airliners. The passenger replied, "Sure, as long as I have my bomb with me." Predicting airplane performance isn't a matter of calculating the odds for a successful takeoff or landing. It's a much more precise game than that. Airplanes have performance charts for all facets of their normal activities: takeoff, climb, cruise, landing, etc. Your success at predicting what will happen during these conditions is a matter of your familiarity with these charts. Machado's ornithological observation states, "All things that fly should use performance charts except birds, since they don't have pockets." Takeoff concepts. Takeoffs are second only to landings for their excitement and challenge. While a takeoff may not be as spectacular for some pilots, in my view it requires just as much research and planning to do it well. Figure 7 shows a typical takeoff profile. At position A, the aeroplane applies full power and accelerates down the runway. It eventually reaches liftoff speed at position B and rotates, which is a fancy word for raises the nose to climb.
One time, Rod forgot to tell a student what rotate meant. At the appropriate point during the takeoff, Rod looked at him and said, "Okay, Bobby, rotate, rotate." The student looked really confused as he thought he was supposed to twirl around somehow. Perhaps as a bizarre takeoff ritual similar to the secret handshake of some flight instructors. The takeoff ground roll is the distance between A and B.
At position C, the aeroplane has attained enough height to clear a 50-foot obstacle. The distance between positions A and C is called the total distance to clear a 50-foot obstacle. Don't you wish all definitions were that easy? Obviously, the taller the obstacle, the greater the distance between A and C. Best rate and best angle of climb speeds. After liftoff is made, you normally want to climb at a speed that will get you to your selected cruising altitude in the shortest possible time. There is one and only one such speed. It is, as I hope you remember from our discussion in an earlier chapter, called the best rate of climb speed, otherwise known as Vy. Figure 8 shows how a climb at Vy might look. The best rate of climb speed will give you the largest upward deflection on the vertical speed indicator. In other words, you'll be able to gain altitude in the shortest possible time. Sometimes climb angle instead of time is a concern during takeoff. Altitude gain for a given distance over the ground is a concern when an obstacle looms at the departure end. Watching an obstacle grow in your windshield is exciting, in the way it's exciting to be a spotted owl at a lumberjack convention. If you want to gain the most altitude for a given distance over the ground, then climb at the best angle of climb speed, otherwise known as Vx. Figure 8b shows a climb profile at Vx. Notice that if the most altitude is gained by the time the airplane has arrived at the obstacle, this represents a very large angle of climb. Even though the nose attitude is generally higher at Vx, the airplane won't have as large a rate of climb deflection on the VSI as it would at Vy. It will initially as you rotate, but then returns to a lesser value. The airplane will still climb at a larger angle because Vx is slower than Vy. With a slower forward speed, it gains more altitude per foot forward distance, making the angle of climb quite large. In many cases, the aeroplane's POH recommends small flap settings to facilitate a short-field climb over an obstacle. The easiest way to remember the difference between Vx and Vy is to ask yourself which one, the y or the x, has more angles. The x has more angles, making it the best angle of climb speed, Vx. By default, y with fewer angles becomes the best rate of climb speed. Vx and Vy change with altitude. The best angle and best rate of climb speeds change slightly with altitude and weight. Since the aeroplane's ability to climb is predicated on excess thrust, in other words power, changing altitude or changing weight or both changes the amount of excess thrust or power available for a climb. This in turn affects the speeds at which Vx and Vy occur. Figure 9 shows a typical rate of climb, ROC, versus true airspeed graph under full throttle conditions. The curve identifies the ROC for different airspeeds at specific altitudes. At full throttle, assumed to be maximum power, there is no rate of climb at point Z since all the aeroplane's power is used to achieve maximum forward speed. As the aeroplane slows to point C, parasite drag decreases and the excess thrust not used to overcome drag, has been converted into a rate of climb. Continued slowing of the aeroplane further reduces the ROC because of the increasing induced drag. At point Y, the aeroplane has no ROC since all the aeroplane's power is used in overcoming an enormous amount of induced drag. This is operating behind the power curve, as described in Chapter 2. The sea level best rate of climb is found at point C. Dropping directly downward to point D identifies the Vy speed for this particular aeroplane. A tangent line from the bottom left corner of the graph contacts the sea level ROC line at point A. At this point, the aeroplane experiences its best angle of climb. Dropping downward from point A to point B identifies the aeroplane's speed for Vx. Why the tangent line? Mathematically, when the beginning of this line is anchored at the graph's origin, the 0 foot per minute 0 airspeed point, it has the steepest slope, largest angle upward, where it contacts the ROC curve at point A. As you can see, Vx is a little less than Vy. As altitude increases, the indicated airspeed for Vx increases slightly, while the indicated airspeed for Vy decreases slightly, as shown in Figure 10. Think about it this way. The smaller one, Vx, gets larger, and the larger one, Vy, gets smaller as altitude increases. Cruise climb speed. Most of the time, it's preferable to climb at some speed slightly above Vy. This is often called a cruise climb speed, and it provides you better forward visibility during the climb, as shown in Figure 8c. On hot days, it also keeps the engine cooler, preventing overheating and possible detonation. The choice of cruise climb speeds is often a matter of pilot preference. Figure 11 shows the rate of climb chart available for some aeroplanes. This chart is for a small two-place trainer. Notice that the rate of climb decreases with an increase in pressure altitude and that Vy is found at a slower indicated airspeed, KIAS, at higher altitudes. KIAS stands for knots of indicated airspeed. Under the rate of climb column are several temperature columns with variable climb rates. Considering how aeroplane performance varies with air density, it shouldn't come as a synaptic shock that the rate of climb varies with temperature. Many POHs don't show the slight increase in the indicated airspeed for Vx with an increase in altitude because the increase is usually small. These handbooks do, however, often show the change in Vx with a change in aeroplane weight. Figure 12a is a short field takeoff distance chart. Section 1, expanded, shows the variable Vx speeds under the 50-foot column. Notice that these speeds decrease with a decrease in aeroplane weight. Vy also decreases with a weight decrease. Remember, at higher altitudes your climb angle at Vx is going to be much less than it would at sea level, despite the fact that you're at Vx. So give yourself plenty of extra margin if attempting to climb over an obstacle off the departure end of a high-altitude airport.
Now, folks, also remember that the airplane is going to climb at less of a rate or angle with the gear down. That's why we retract the gear as soon as it's safe after departure, usually when there's no runway left on which to land. Flaps are sometimes used for takeoff when suggested by the pilot's operating handbook. The important thing to keep in mind about flaps is that they usually shorten the ground run but reduce the angle or rate of climb. Not always, but sometimes. Check your pilot's operating handbook to determine if they do. They should be retracted after liftoff when the airplane is accelerated to the recommended climb speed.
Takeoff distance chart. All aeroplanes have some takeoff and landing performance charts. Figure 12b is a typical example of a takeoff distance chart. With your first glance at this chart, you probably feel as confused as a far-sighted Venus flytrap that's just ripped the fly off somebody's pants. Not to worry, I'll explain how to use it, the chart, not the flytrap. This chart provides you with your takeoff ground roll under variable airplane and airport conditions. It also provides the best angle of climb speeds based on various weight conditions. Learning how to use this chart is best done by example. A hint when using this and other performance charts. Many performance charts require that you slide up and down calibrated lines on the chart when moving from one reference point to the next. Movement along these lines should be proportional, not parallel. Figure 13 provides you with a good idea about how to do this. In those cases where a performance chart's calibrated lines are close together or appear parallel, then move parallel to these lines. Takeoff distance example number 1. Using the takeoff distance chart in Figure 12b, what is your ground roll and distance to clear a 50-foot obstacle based on the following conditions? Outside air temperature, OAT, is 59 degrees Fahrenheit, 15 degrees C. Pressure altitude is 5,650 feet. Takeoff weight, 2,950 pounds. Headwind component, 9 knots. First, find 59 degrees Fahrenheit, 15 degrees C, on the bottom of the chart in Section 1. Move directly to the 5,650-foot pressure altitude line, Section 2. You'll have to estimate where 5,650 feet pressure altitude is, just like you did with the density altitude chart in Figure 3. Use the following method. The 5,000-foot pressure altitude line is halfway between 4,000 and 6,000 feet. Draw a hair-thin proportional line between these altitudes. It stands to reason that the 5,650-foot pressure altitude line is a little above a point halfway between the 5,000-foot line and the 6,000-foot line. Now, move horizontally to the right, directly over to the dark, vertical reference line in Section 3. As you move horizontally on the chart, simply follow the nearest grid line to avoid making mistakes. In Section 3, we'll correct for weight. Since our weight is 2,950 pounds, and this is what the reference line rests on, no correction is necessary. Simply move right, horizontally, to the next reference line in Section 4. If we did have a weight different from 2,950 pounds, we'd move proportionally to the diagonal lines until reaching our takeoff weight shown on the bottom scale in Section 3. Then we'd move right, horizontally, to the reference line in Section 4. Now, it's time to correct for a headwind or tailwind component. We have a 9-knot headwind component, so we'll move down, proportionally, to the nearest diagonal line until reaching a 9-knot wind component value shown on the bottom scale of Section 4. From this point, we'll move horizontally to the right toward the next reference line. If we had a tailwind value, we'd move up and proportionally to the nearest sloping dashed line until reaching the appropriate wind component value. Then, we'd move horizontally to the right toward the reference line. At the reference line in Section 5, we can determine our takeoff ground roll by moving horizontally toward the right. The numerical value of approximately 1,375 feet, listed at Section 6, is our takeoff ground roll. This is only our ground roll, not the distance required to clear an obstacle at the end of the runway.
Now, men, if an obstacle exists at the end of the runway, we can determine how much horizontal distance is required to clear the obstacle. Let's assume we have a 50-foot obstacle at the end of the runway. Move up and proportional to the diagonal line nearest Section 5 until reaching the 50-foot height mark on the bottom scale. Obstacle heights are calibrated by the scale at the bottom of Section 5. When reaching the obstacle height shown horizontally along the bottom of the chart, 50 feet in our case, look horizontally to find to the right. 2,300 feet of horizontal distance is required to clear that obstacle. Section 6A. Keep in mind that this is just to clear the obstacle. Your tires could just scrape the bottom of that obstacle, possible thumping some bird on his head. Maybe that's how bald eagles got bald.
There are several other interesting things you should know about this chart. First, in Section 7, there is a list of takeoff speeds for different weights. At 2,950 pounds, we want to lift off at 66 knots. If there is an obstacle at the end of the runway, then we want to climb at a speed of 72 knots for that weight. Variable weights require different lift-off and obstacle climb speeds. Second, Section 8 lists all the associated conditions this chart is based on. Machado's inverse law of chart conditions says, "The notes on a performance chart will be of value to you only when you forget to read them." Notes at the bottom of performance charts are the fine print of aviation. Always make it a point to read all the conditions listed in this section of a chart. There are many little variables affecting aeroplane performance listed in this section. Notice that the engine must be leaned to the appropriate fuel flow indications during takeoff. This assures maximum power is developed. Also, the gear is assumed to be retracted immediately after a positive rate of climb is established. This is done, obviously, if there is an obstacle to clear. Normally, without an obstacle, you wait until there is no more runway on which to land before raising the gear. Of course, if you are attempting to retract your landing gear on an airplane that isn't of the retractable gear type, then I want you to reread those directions on the back of your code medicine. Takeoff distance problem number 2. Refer to Figure 12b and determine the ground roll and total distance required for takeoff to clear a 50-foot obstacle based on the following conditions. OAT outside air temperature, standard conditions. Pressure altitude, 4,000 feet. Takeoff weight, 2,800 pounds. Headwind component, calm. Figure 14 shows how this problem is solved. ISA stands for International Standard Atmosphere and means the same thing as the term standard conditions used by U.S. engineers. Just find where the ISA line, standard temperature line, intersects the 4,000-foot pressure altitude line and move right horizontally to the next reference point. Approximately 1,050 feet are required for the takeoff ground roll, and 1,750 feet of horizontal distance is required to clear a 50-foot obstacle. Be careful when you are moving horizontally across the chart. Make sure you move parallel to one of the horizontal grid lines, thus minimizing the chance of error in chart reading.
Cortez, when he discovered the New World, burned his ships. As a result, his crew were well motivated. Frankly, there is a time when you might use the standard temperature or ISA line when computing airplane performance. You may want to estimate how the airplane will perform at a given altitude without knowing the actual outside temperature. such as when making rough estimates as to the total weight, fuel, payload, etc., that you can depart with. Simply find where the ISA line intersects the elevation of the departure airport. Since you don't know the temperature and pressure altitude, this gives you a rough way to anticipate airplane performance. Remember, this is only used as an approximation.
You know something, Sean? I still have a feeling that some of those mischievous 8th century monk scribes got loose from the monastery, became performance chart engineers, and inserted these ISA or standard temperature lines in the airplane performance charts.
Takeoff distance problem number 3. Refer to figure 12b and determine the ground roll and the total distance required for takeoff to clear a 50-foot obstacle based on the following conditions. OAT, 100 degrees Fahrenheit. Pressure altitude, 2,000 feet. Takeoff weight, 2,750 pounds. Tailwind component, 5 knots. Figure 15 shows how this problem is solved. The only significant difference with this problem is that a tailwind component exists. We must move upward, proportional to the dashed lines in section 4 in figure 12b. From there we proceed to the next reference line. A ground roll of approximately 1,300 feet is required, and 2,150 feet of horizontal distance will be used to clear a 50-foot obstacle. At this point, you're probably wondering why the Federal Aviation Administration puts up 50-foot obstacles at all these airports. All these questions make it seem like obstacles are mounted on mobile dollies, towed to different airports, like the old MX missile program, and placed on the departure end of runways to test the skills of a pilot. Well, this isn't true, but it is interesting to consider that most of these obstacles are represented as trees. If that were so, it would seem logical that those obstacles would get smaller whenever pilots, ignorant about takeoff performance charts, depart that runway. In other words, they'd be 50-foot obstacles at first, then the following week they'd be 46-foot obstacles, then 38-foot obstacles, and so on. Eventually, the FAA would have to tow in a new obstacle. Fortunately, pilots do a good job in avoiding obstacles. A different takeoff distance chart. Figure 16 shows a takeoff distance chart for a small two-place trainer. As with all performance charts, read the notes before doing any computations. Short field computations are based on 10 degrees of flaps, full throttle, then brake release, specific runway conditions, and 0 wind. Note, number 3 states that distances should be decreased 10% for each 9 knots of headwind. For tailwinds up to 10 knots, increase distances by 10% for each 2 knots. If you're taking off on a dry, grass runway instead of a hard surface, we need to increase distances by 15% of the ground roll. Grass creates drag and prevents acceleration of the aeroplane. If there are groundhogs hiding in the grass, these might also inhibit acceleration. You'll never see a chart that says to add 5% for each suspected groundhog. You'll notice there is no chart variation for different weights. That's because a small two-place trainer doesn't have much variation in its payload compared to a larger multi-seat plane. Takeoff distance problem number 4. Using figure 16, determine the takeoff ground roll and distance to clear a 50-foot obstacle based on the following conditions. Pressure altitude, 3,000 feet. Temperature, 20 degrees C. Tailwind component, 4 knots. Without correcting for the tailwind, we obtain a ground roll of 1,000 feet and a distance to clear a 50-foot obstacle of 1,870 feet, according to Figure 16. Note, number 3 on the top of Figure 16 states we need to increase our distances by 10% for each 2 knots of tailwind. Our calculated distances need to increase by 20%. Based on the computations in Figure 17, our expected ground roll becomes 1,200 feet, and the horizontal distance to clear a 50-foot obstacle becomes 2,244 feet. Takeoff distance problem number 5. Using Figure 16, determine the takeoff ground roll and distance to clear a 50-foot obstacle based on the following conditions. Pressure altitude, 3,500 feet. Temperature, 10 degrees C. Headwind component, 18 knots. Notice that the pressure altitude is halfway between the 3,000 and 4,000 foot values. There are several ways to go about solving this problem, and a little interpolation is necessary. Here's one way, as shown in Figure 18. Determine the ground roll and distance to clear a 50-foot obstacle at 3,500 feet by adding the 3,000 and 4,000 foot values in the 10 degree C column together, then dividing by 2. You should get 973 feet, rounded off, for the ground roll and 1,825 feet for the distance over a 50-foot obstacle. We could stop here if it were not for the 18-knot headwind. Note number 3 in Figure 16 says decrease distances 10% for each 9 knots of headwind. This means we must decrease both values by 20%. According to Figure 18, this gives us a 778-foot ground roll and 1,460 feet to clear a 50-foot obstacle. Be careful when applying corrections for headwinds or tailwinds. You must remember to subtract takeoff distance values for a headwind and add these values for a tailwind. Headwinds decrease takeoff distance and tailwinds increase them. Sometimes it will be necessary to interpolate for both pressure altitude and temperature when using these charts. If you find yourself close to any whole number value for temperature or pressure and feel it's difficult to interpolate, then use the larger whole number value. This gives you a slightly longer takeoff and obstacle clearance distance, but at least it errs on the conservative side. Landing distance performance charts. Remember as a kid watching movies in school, on days when the teacher didn't feel like teaching? Sometimes the film would jam, and after straightening it out, they'd run it backwards a bit so you didn't miss any morsels of knowledge. We're about to do the same thing. A landing chart is a takeoff chart in reverse. Instead of launching over a 50-foot obstacle, you're assumed to be landing over one. Once again, there's the distance over the obstacle to the point of touchdown, and there's a ground roll to account for. Figure 19 shows a typical landing distance chart. Notice its similarity to the takeoff chart used in Figure 12b. This chart is used in exactly the same way as Figure 12b. Remember, we're just running the movie backwards. Keep in mind these distances for landing over a 50-foot obstacle assume that you barely clear the obstacle as shown in Figure 20. You may assume you will always clear an obstacle by more than just inches, but the chart doesn't assume that. To be practical and safe about this, add a few more feet onto the values shown in the chart. In other words, you shouldn't be landing with branches or twigs protruding from the wheel pounce. Let's try the following problems. Landing distance problem number 1. Using the landing distance chart in Figure 19, and based on the following conditions, determine the total distance required to land. OAT, 32 degrees Fahrenheit. Pressure altitude, 8,000 feet. Weight, 2,600 pounds. Headwind component, 20 knots. Obstacle, 50 feet. Before using any performance chart, always read the conditions listed on the chart. Section 8 in Figure 19 lists the conditions under which the landing is conducted. Section 7 lists the approach speeds you should be using to obtain performance chart values for your landing. I also like how it lists gear down as one of the conditions. Remember, if you forget to put the landing gear down, your landing distance will be cut by approximately 99%, but your maintenance bill will go up considerably. Figure 21 shows how I computed the answer. Notice, the headwind components require that you slide down diagonal lines shown in Section 4 of the chart. Sliding downward decreases your final distance value, while sliding upward increases any landing value. You need 1,400 feet of horizontal distance to clear a 50-foot obstacle situated on or near the end of the runway. From the instant you cross the obstacle at 50 feet until the time you come to a stop on the runway, you'll need 1,400 feet of distance. Of course, this assumes, according to Section 7, that at 2,600 pounds of weight, you cross the obstacle at an indicated airspeed of 65 knots. Any faster, and the landing distance will increase. Landing distance problem number 2. Using the landing distance chart in Figure 19, determine the total distance required to land based on the following conditions. Outside air temperature, standard. Pressure altitude, 2,000 feet. Weight, 2,300 pounds. Headwind component, calm. Obstacle, no obstacle. According to Figure 22, you'll need an 850-foot ground roll under these conditions. This is the distance required to stop from the time the aeroplane touches down. A different landing distance chart. There are certain things you just never do. For instance, never put the word yes on a job application on the line that says salary expected. When being interviewed as a police officer candidate and asked why you want this job, you should not say, "The lights, man, I love all the lights." There's one thing you never do when working with a landing distance chart. You should never assume that all landing distance charts are the same. These charts come in several shapes and flavors. The chart shown in Figure 23 is another version of a landing chart. Once again, before using any chart, look at the notes and conditions listed on the chart. Notice that note number 1 says we must decrease distances by 10% for each 4 knots of headwind. We must increase distances by 10% for every 60 degrees Fahrenheit temperature increases above standard. Standard temperatures are those listed next to the altitudes in each chart column. 60 degrees is a rather large temperature jump. If temperatures are only 30 degrees Fahrenheit above standard, increase distances by 5%. Notice that in note number 3, landing distances on dry, grass runways increase all calculations by 20%. If dry, grass runways increase our takeoff distance, shouldn't they also decrease our landing distance? Not really. Braking is much less efficient on grass, even if you are conking gophers on the head. Delicate braking is required to slow the aeroplane, making stopping distances much longer. Read the note carefully. Let's try a few of these problems. Landing distance problem number 3. Using the landing distance chart in Figure 23 and based on the following conditions, determine the total distance required to land over a 50-foot obstacle. OAT Standard. Pressure altitude 7,500 feet. Headwind component 8 knots. Runway dry grass. Based on a pressure altitude of 7,500 feet and a standard temperature of 32 degrees Fahrenheit, our landing distance over a 50-foot obstacle is 1,255 feet. With a headwind of 8 knots, we need to decrease our distance by 20%, according to the chart note number 1. This gives us a ground roll of 1,255 minus 20% of 1,255, equaling 1,004 feet. Our last correction is for a dry grass runway. Note 3 states we must increase all distances by 20% of the total to clear a 50-foot obstacle distance. This gives us a final value of 1,004 plus 20% of 1,004, equaling 1,204.8 or 1,205 feet. Landing distance problem number 4. Using the landing distance chart in Figure 23 and based on the following conditions, determine the total distance required to land over a 50-foot obstacle. Outside air temperature 101 degrees Fahrenheit. Pressure altitude 5,000 feet. Headwind component calm. According to Figure 23, an altitude of 5,000 feet and 41 degrees Fahrenheit produces a distance over a 50-foot obstacle of 1,195 feet. Our temperature is 60 degrees Fahrenheit, more than standard for that altitude. According to note number 2, we need to increase our landing distance by 10%. This gives us a 50-foot obstacle clearance value of 10% of 1,195 plus 1,195, equaling 1,315 feet. Never forget Machado's calculation canon. The most important part of the body to use in calculating takeoff and landing distance is the brain, not the wishbone. Time, fuel, and distance to climb chart. Another flavor of chart useful in flight planning is the time, fuel, and distance to climb chart shown in Figure 24. As always, read all the notes before using the chart. Notice that the columns provide you with a climb speed, the best rate of climb, speed Vy, an expected rate of climb, the time it takes to climb, fuel used in gallons, and distance covered, assuming zero wind. The chart shows how Vy decreases with an increase in altitude. Climb problem number 1. Using Figure 24, estimate the amount of time and fuel consumed to climb from sea level to 5,000 feet pressure altitude under standard temperature conditions. This is a relatively easy problem to solve. First, look at the fuel used and distance values for the 5,000-foot pressure altitude row. This gives you 8 minutes and 1.2 gallons of fuel used. Adding 0.8 gallon of fuel per note number 1, we find that we consume 2.0 gallons of fuel while taking approximately 8 minutes to climb once airborne. That's easy. So let's make it a little more practical and challenging. Climb problem number 2. Using Figure 24, estimate the amount of time and fuel used to take off and climb from an airport with a pressure altitude of 2,000 feet to 6,000 feet pressure altitude, when the temperature at the airport is 21 degrees C. This problem requires us to subtract the difference in time and fuel consumed from 6,000 feet to 2,000 feet. This gives us a time to climb from 2,000 to 6,000 feet pressure altitude of approximately 10 minutes minus 3 minutes equaling 7 minutes. We also derive a fuel consumption of approximately 1.4 gallons minus 0.4 gallons equaling 1 gallon. The last thing we do is make a correction for the non-standard temperature. Since 21 degrees C at 2,000 feet is 10 degrees C above standard temperature for that altitude, per note number 3, we should increase both these values by 10%. Our time to climb value becomes 7 minutes plus 0.7 minutes equaling 7.7 minutes. Our fuel used value becomes 1.0 gallon plus 0.1 gallon equaling 1.1 gallons. We do, however, need to add that 0.8 gallon according to note number 1 for engine start, taxi, and takeoff. This gives us a total fuel consumed of 1.9 gallons. This is a very handy little chart to use. You'll find it very useful for cross-country flight planning purposes. Although we didn't compute the distances covered during the climb, this is easily done using the same method described in Chapter 14, page N32, under the section titled A More Accurate Flight Plan.